All right, any questions about anything before we get back into things? All right, so been talking about trig substitution for a couple of days now. Might finish it up today, but there's a lot here. So one of the things we talked about, I think we just did this one example with last time, is where you have this integral that doesn't obviously, it's not obvious that a trig substitution is going to help you get through it, but that's kind of what we're after. So one thing I want to make sure we have going forward is that, so the substitution we chose for this one was that x equals sine theta. Why was that useful? What did making x equal to sine theta help us do that made this integral possible in the end? Go ahead. Right, so basically you collapse those two terms under a radical into one. So basically that's going to be kind of our guide going forward. So moving on, maybe. Here we go. So same kind of question here. I want to know what x is going to be equal to. That's going to cause that radical, basically cause the terms of that radical to become one. Any ideas? 3 sine theta? Where'd the 3 come from?
Because you're going to need to get down to 1 minus sine squared of theta. So you want to get the 9 out of there.
Okay.
So if we're going to do x squared, that means 3 will also be squared and sine will be squared.
Okay. So how about the sine? I mean, we didn't change that from last time, right? So what about this? So I understand why you said 3. Why is the trig function we're calling for? Why is that sine still?
Because the Pythagorean identity of 1 minus sine squared equals cosine squared.
Okay.
Which means that we actually take the square root once we're able to do the substitution.
Okay. So because I was expecting this to come up, I'm actually going to delete this 3 for now. To show what happens. But I think, yes, it has the same form where I have a number minus the variable squared, which just like the last one, we use sine. So if I do that, let's just go back to sine theta for now. If x is sine theta, what's dx? Cosine theta. So what happens if I try to apply that substitution here? I get 9 minus sine squared theta over sine squared theta times cosine of theta d theta. So again, one of our major goals here is to get that expression under the radical in a form that can be reduced to a single term. I don't think that happens if we just have x equal to sine theta, right? There is no Pythagorean identity that allows us to deal with 9 minus 9 squared or 9 minus sine squared theta. So if we make the change that, the thing that was first suggested, if we make x equal to 3 sine theta, then what's dx equal to? 3 cosine theta d theta. And then we don't get this integral, we get what instead? We get the integral of radical 9 minus 9 sine squared theta over 9 sine squared theta times dx, which is 3 cosine theta d theta. So substitution is done, but now is it actually a substitution that can help us? What in here can I simplify, if anything? Go ahead. If you do x equals cosine theta? Right, so I will tell you this, doing this as a cosine will also work. for the same reason that this works. Basically, what's 1 minus cosine squared theta? Sine squared theta. So because of that, you know, we have this form. This basically under the radical, we have a constant minus a variable squared. Sine or cosine, either one will work there. Okay, so now this kind of nasty looking integral we have now, can anything in here be simplified to help us move forward? Okay, if I factor out the 9, let's see what happens. Under the radical, I have 9 times this quantity, 1 minus sine squared theta. Leave everything else alone. Did that make it clear that the radical is now going to be something we can get rid of? Right, so the identity makes the 1 minus sine squared theta equal to cosine squared theta, right? So in this radical, actually, maybe I'll not skip any steps here. Give myself more room. The square root of 9 cosine squared theta over 9 sine squared theta times 3 cosine theta d theta. If I resolve that square root now, then what do I get? I get 3 cosine theta over 9 sine squared theta times 3 cosine theta d theta. Did that help? What now? Okay. How does it reduce now? Okay. So cosine squared theta over sine squared theta d theta. Is that an integral I can do? Go ahead.
Step before that, when you factored in the 9,
Mhm.
where did the other 9 go? Because you had 9 minus 9 sine squared.
Right. So here, basically, I factored a 9 out of both these, right?
Okay.
So if I divide 9 by 9, I get 1.
Okay.
And 9 sine squared theta divided by 9 is 1.
Okay. And then for the most recent step, I just simplified the cosine squared.
So the 3 and the 3 combine. 3 times 3 is 9.
Oh, okay.
So basically this, not obvious because they're at different levels, but 3 cosine squared, 3 cosine theta times 3 cosine theta.
Okay.
All right, so what does this become? That is true, but I'm going to push back on that.
I'm not sure if it'll help.
What's that?
1 minus sine squared theta.
Same kind of thing. And also, here's and this, like, we're illustrating what's really hard about this topic. You have lots of choices, all mathematically correct. Some are just going to be chasing your own tail. So what I'm going to push us toward is this, and maybe it won't be obvious, but we'll talk about why I'm doing it. Can I call this cotangent squared of theta d theta? But why? Why is that something I would push you toward? What's what? It's one term, which is only really useful if we can integrate that one term. Can we integrate that one term? Do we know what the integral of cotangent squared is? I don't think so, but we have lots of other trig identities we can go with, right? So let's go back to this one. Cosine squared theta plus sine squared theta equals 1. And something we've done in the past is divide everything by cosine squared. But what happens if I divide everything by sine squared? Then I get cotangent squared of theta plus 1 equals cosecant squared of theta. is the integral of cosecant squared of theta. You're something you remember. That is cotangent. Actually, or is it negative cotangent? Negative cotangent. So again, with this trig substitution, a lot of times you have these integrals which are totally accurate, mathematically accurate, but maybe not accessible. But I think most of you, if not all of you, know that the integral of secant squared of theta is tangent squared of theta, and probably not as well known as that the integral of cosecant squared theta is negative cotangent theta.
Could you use a half angle?
And that's another good news and bad news, right? Probably also was a place where a double angle identity would have got us to the end here. A lot of different ways to approach these. So, oh, minus theta. Let's see. So probably a lot to revisit and talk about here. How are we doing? What questions do we have?
I'm kind of confused, so mine just added like the dx onto that at the very beginning.
The dx onto the end?
Yeah.
Well, that's part of the integral. Remember that when you integrate, you have your integrand, your function you're integrating, but also think back to the way you developed a Riemann sum.
So it doesn't have to be in the equation to begin with.
The dx?
Yeah.
What equation are you referring to?
So the 3 cos theta doesn't have to be explicitly stated in the equation.
No, in fact, that comes from the substitution that we make. And again, this is kind of a strange thing because every other substitution we've done has been where we take, try to figure out what our u is. Usually the way we do this, we take something complicated and condense it into a thing we call u. Now we're kind of doing the opposite thing. And I might have said this after class, not during class, but now we're kind of doing the opposite. We're taking the simplest form of the variable there is, right? Which is x. And we're saying that's equal to something more complicated, 3 sine theta. So because of that, the dx becomes more complicated as well. But yeah, no matter what kind of substitution you're doing, you have to substitute both for that base variable x or whatever it's called, usually x, but also you have to make the substitution on dx as well. Good question. Anything else about this?
I just have a question on the d theta.
D theta.
You, to bottom.
Mm-hmm.
So you integrate the cosecant as negative cotangent. What happens to the d theta? Do you not have to put the value of the d theta from dx?
No, because, and this is, it's kind of a cop-out answer, but it's kind of a matter of convention. When we do the substitution in this direction, we don't typically have to go backward. So because of that, I'm going to leave it in terms of theta and call that okay.
The web work does want us to go back.
They do?
Yeah.
Okay. I hate that.
So like for theta.
So in that
we
case,
have to do the
let's talk about it then.
or something.
If x is equal to 3 sine theta, then what's theta equal to?
So 3 parts of the
The inverse sine of what? X over 3. So sort of annoying. I don't think I realized the web work was built that way. But that is the one thing you'll have to do on top of what I'm doing here. So basically, if they want you to put your final answer back in terms of x, then you'll have to come up with this substitution here. Because like we defined what x was equal to in terms of theta, but basically this is the inverse of that. Basically solve that substitution you made, solve it for theta.
So if you plug that into
Yeah, so do I have enough room to actually do it? So negative cotangent of the inverse sine of x over 3. The answer is no, but I'll try it anyway. Minus the inverse sine of x over 3 plus c. And maybe that illustrates why we don't usually go back, because now you took your simple thing and you traded it in for something that's more complicated. Question?
On an exam, would we be allowed to leave it in terms of data?
I'll promise you that much. Anything else? Go ahead.
So just in general, should we just like memorize all the integrals of the squared and trig functions?
Of those two for sure.
Of which two?
The secant squared and cosecant squared,
Okay.
because those have pretty simple integrals. The integral of secant squared is tangent theta. The integral of sine squared is something I know I could do, but I don't know if it's worth you committing to memory. I think it'd be more valuable if you knew, like, well, I know I have the double angle identities. I could rebuild it, but here's the thing: if you try to memorize it, you might feel good about memorizing it, and then on the day you need it, a negative sign in your head gets flipped or something. All right, any other questions about this beast that we just got through? All right, what if we have something a little different? So again, we're going to focus first on what's under the radical, but now I have, basically there are three major forms you're going to deal with. And the first one we just dealt with in the last two examples, which were what? I think the book kind of a squared minus u squared, right? So basically, a is a constant. And u is something variable. And in those cases, what did we use for the u? Or what trig function was it a form of? So basically, in this case, we said u is equal to sine of theta, right? And specifically, a sine theta. Because u, that constant is the only thing that helps you bring that Pythagorean identity in to do that simplification. So now what we want is this. We want a trig identity that will allow us to reduce this. Basically, we have this new form of what? U squared plus a squared. I got to vote for tangent. Why is that? If it's just a guess, we can go with it and try it. See what happens.
Substitute tan squared of theta plus 1 for secant squared of theta, which we can.
Okay. So what is the tangent squared of theta equals what?
Is equal to
Minus 1, which means secant squared of theta is equal to tangent squared of theta plus 1. And I think this is really important for illustrating why that's going to get you to where you want to go. That'll become clear when we actually make the substitution. So we want to use x equals tangent theta? 2 tangent theta. Questions about why I think 2 is better than 1? That's a good question here. So yeah, what about what's under the square root is leading us towards 2 tangent theta instead of just 1 tangent theta?
It'll be squared.
Right, so it's that 4 here that's driving that. So basically, when I square that x, it'll become 4 tangent squared theta plus 4, which I can do something about, but as opposed to tangent squared of theta plus 4, which I don't have an identity that's going to get me something simpler there. So let's try 2 tangent theta. Then what is dx equal to? 2 secant squared theta d theta. So let's try substituting now. This becomes the integral of 1 over what? Two tangent theta?
Squared, so 4
Yeah, so I'll just leave it like this for now. And then times the square root of times dx, which is what? 2 secant squared theta d theta. So again, our substitution, at least initially, makes everything look more complicated. So now it's up to us to start simplifying. Can we do anything?
Substitute for secant squared theta.
Substitute what? I'm sorry.
For secant squared theta. Right?
Where's that?
Under the-
Oh, yeah, under the radical. So under the radical, maybe this is just the only. Still getting the hang of this, so maybe I'll do this in a few steps. 1 over, I'll call this 4 tangent squared theta times the square root of 4 times tangent squared theta plus 1. So under the radical, I think that'll become 2 secant squared, right? 2 secant squared theta. So 1 over 4 tangent squared theta times 2 secant squared theta, 2 secant squared theta d theta.
Would it be secant first?
What's that?
Would it be secant first?
Yes, thank you. All right, now what? That's but what do we want to do first? There's probably lots of ways we could do it. What simplifies?
2, say, secant.
Okay, so what do we have left? We have the integral of secant theta over 4 tangent squared theta d theta. Really shouldn't have written so large. So what might we do now?
Either substitute secant for u or tan for u, but I forget which one we use when.
Okay. So you want to jump and do another u sub?
Thing.
If u is equal to secant, then what's du equal to?
Get,
Secant tan, which, yeah, I don't think that'll work.
I'm not gonna get secant squared, so never mind.
Okay,
Ignore
so
that suggestion.
I don't, so here's the main, but it's good to talk about it. I don't think secant or tangent for u is going to basically make the rest of this pop up. Anything else we might try?
Sine, cosine, see what we end up with.
Let's do that and see what comes out of it. So what is secant in terms of, okay. So this is equal to 1 over cosine theta. And what is tangent equal to in terms of sine and cosine? I'm going to reciprocate that. Yeah. So cosine squared theta, left off of 4, didn't I? All right, did that help?
You can reduce the.
So I have some cosines that'll cancel, right? So now I have the integral of, yes, 4 cotangent, but for now I'm going to write it as 4 times the integral of cosine theta over sine theta d theta.
Sine squared.
Oh, it is. Didn't budget my space well. What can we do from here?
With the space, or could we just change it into cotangent cosecant? Because isn't that the derivative of cosecant?
Okay, so I heard a couple things there. I'm going to try to write them both down. So what's the derivative of cosecant of theta?
negative cosecant of theta times cotangent.
If that's something you remember, then we can use that. What was the other thing you mentioned?
U equals sine squared, or U equals sine of theta.
If we do u equals sine theta, let's see if this substitution helps. If u equals sine theta, then du is cosine theta d theta. What does that do to this integral? So it's the integral, so 4 times the integral of, what's that? 1 over u squared. Feels too good to be true, but I think it's true. So I'm going to stop here just to gauge how we're feeling, because there was a lot of different paths we took and a lot of different paths we talked about that we ended up not using. So questions about the choices we made, anything at all? Go ahead.
Well, so what was the thought process on choosing 2 tangent theta for x?
2 tangent theta. That's a good question. So why did we make this choice originally? I'll break that into 2 pieces. Why did we choose tangent instead of any of the other 5 trig functions?
Because tangent is the only one that you can add to 1 and make a substitution for 1 variable that we could take the.
Right, and that's basically it, is that we have this form where basically underneath the radical, what do we have? We have two quantities added together. So we're going to look for Pythagorean identity that looks like that. In this case, I don't think it's the only one, but like I think cotangent squared plus 1 gives you cosecant squared, right? But I think tangent is a better choice. The integrals come out a little cleaner. So that is why we chose the tangent. Where did this constant 2 come from? 2 squared, you get 4. And that is really driven by this added constant under the radical here. So that's where our original substitution scheme came from. What else? Go ahead.
Would there ever be a time in which you have like a 1 over, something similar if you like discarded the x squared and for the radical, where you could like just change it into one of those like derivatives of like sine and cosine?
Yeah, so I mean that's the thing, like if this was gone, I think this I don't know if it's direct. I don't know if this is directly work as one of those inverse trig ones, but yeah,
But you would be able to-
you're right to notice those things because sometimes they pop up out of this.
Okay.
And if you notice them, it makes the integral a lot cleaner. Anything else?
On an exam, would we be guided like in the directions to use trig substitution, or do we use integration by parts?
In the past, in the past, that's all I can tell you. I don't know. I can't promise you going forward, but in the past, we have said use trig substitution to do this. It's still then on you to figure out which of the many trig substitutions is correct, but in the past, that's what we've done. What else? Can we integrate 1 over u squared du? What is it?
4/3. No, never mind. Sorry.
I know where you were going.
Yeah.
Maybe it's so. I think that illustrates that
over,
it's probably better to do this.
Yeah.
So what's that integral of u to the negative 2 du?
-4 u to the -1.
Negative 4 u to the -1 plus c. So now we got like 2 layers of substitution here, right? What was u? So -4 over sine of theta plus c. Or if you'd rather, -4 cosecant theta plus c. Questions? Go ahead.
It's just a detail, but if we had 4 tan squared of theta, then before we like attach the sine of sine with the sine, so it'd be 4 the constant instead of 4.
Oh, so you're asking it should be over 4 instead of,
Yeah, I'm just making sure I'm not.
I believe it should be 4 because that power of -2 only applies to the u, not to the 4. Or did I misunderstand you?
4 tan squared theta, so that's 4 sine squared theta over cosine squared theta. You have 4 cosine squared theta over.
Oh, have I been carrying the 4 in the wrong place the whole time?
No, because when you multiply by the reciprocal, the 4 also got brought up. Or no, but it shouldn't.
No, it shouldn't have.
It shouldn't have, so you're
Okay,
right.
thankfully that's an easy thing to repair. I'm glad that you caught that before we moved on, but this should be a 1/4. Is it okay if I just repair it at the end? And actually, no, it's not okay. It's not okay. But I'm gonna get lazier and lazier about it as I go. Good catch on that. Go ahead.
Is it fine to say not for cosine because you swap to cotangent?
I'm sorry, I lost you. Is it okay to do what?
Isn't cosine over sine, is that cotangent or tangent?
Cotangent.
So then you're swapping into cotangent, so the force will get the top. Bottom.
I don't think so because the changing the cosine and sine to cotangent that doesn't have anything to do with that coefficient.
Okay.
I think we're okay. But
How did you go from the 1/4 sine theta to cosine theta?
1/4 sine. 1/sine theta is that's the definition of cosine theta. So and I want to point this out is so even though I boxed the last one I did, I don't have any problem with this one above it. Those are exactly equivalent. What else? Okay. How many more of these do I have? I do want to make sure I do. Let's flip the order on these. So, is this like either of the ones we've talked about before? So we had this form, right, where the constant comes first in a subtraction. The one we just did was this u squared plus a squared. This is not like either of those, right? So this is something new. Still subtracting, but instead I have the variable coming first. So now I want to come up with I need to figure out a new approach. Still going to involve a trig function, but what is that trig function going to be? Got to vote for secant. Which one are you saying? Secant or tangent?
Oh, secant.
Okay.
But that's would be-
Oh, I see what you're saying. Okay. So if we try x equals secant theta, do you want secant theta or something a little different? Let's try this and see what happens. If x equals secant theta, then what's dx equal to? Secant theta, tangent theta, d theta. So let's look at the Pythagorean identities again and see if this gives us any idea about whether this is going to work. So if I divide everything by cosine squared, I get 1 plus tangent squared theta equals secant squared theta. Let's solve for the one we actually wanted to do. Oh, no, it's already solved that way. So if we do x equals secant theta, how do we feel about going forward with that? Last chance to change your mind. Okay, let's try the 10. So that's just going to so let's see what happens if we make this substitution. So this integral becomes the integral of 1 over the square root of 100 secant squared theta minus 100 times dx, which is 10 secant theta tangent theta d theta. Did this help? Is there anything we could do to see if it got us to where we wanted to go? I haven't asked this question in a while, but what's our goal here? Like one of our first, like what's going to tell us whether or not this substitution worked? If you can cancel out that radical. And what's going to help us cancel out that radical?
If after the, if it becomes secant minus 1, then it would tangent.
Okay. If I factor out 100, then I get secant squared theta minus 1 What is secant squared minus 1? Anything convenient? That is equal to tangent squared. Good. So I think because of that, yes, that substitution was the right way to go. So now I get 10 secant theta tangent theta over 10 times tangent theta d theta. So that gives us what? The integral of secant theta d theta. Is that something I can do? Yes. But how?
You
Okay.
can multiply by secant of theta plus tan of theta over secant of theta plus tan.
That is a way to do it. Unfortunately, I think that's the most direct way to do that. I would prefer this though. What is the integral of secant theta? Someone look it up.
The natural log of the absolute value of secant of theta plus tangent of theta.
Okay. Obviously, right? So yeah, I mean, I can briefly kind of talk about where that comes from, but it comes from this totally unintuitive manipulation here. Basically multiply secant theta by secant theta plus tangent theta over secant theta plus tangent theta. And that gives rise to a substitution that makes that possible. But yeah, very, very not obvious. The biggest thing I want to focus on here is the fact that, you know, we have all three of these, you know, presentations now. And basically, when we're talking about trig substitution, it's really limited to these three cases. Basically, what's under the radical? What form does it take? So now that we've done all three, do we have an idea as to which one signifies what trig function you should use? So I think we said sine here, right?
Tangent.
And secant. And all three of those things come from,
Looks like the inverse, like there's 1 over. It kind of is.
yeah, and that,
Yeah, the inverse functions.
right, and that's not an accident. That's why, basically, that's what allows that radical to be simplified. Any questions here? All right, so now that you've seen all three, let's go back one, and let's end on this. What should we start thinking about?
Look at the. It would be tangent. tangent because of the formula that we just kind of figured out.
right? So x equals tangent theta, right? 2 tangent theta. So let's just recap. Where did the tangent theta come from? Basically, we're adding, basically we have a sum in the under the radical. And the 2? Right, so basically, yeah, square root of 4 is 2. And even though we didn't really talk about it here, that's why that's where the 10 came from, and square root of 100. All right, so if that's our x, then what's dx? Theta. All right, using that, then what does our integral become? That it? That's 2 secant squared theta e theta. Good. Now what? You take out the 4. Now 2 tangent theta over 2 times the radical of tangent squared theta plus 1. So factor that a little differently than last time, but it works. Times 2 secant squared theta d theta. Good. What else? Right. So tangent squared theta plus 1 is equivalent to secant squared theta. Square root of secant squared theta is secant theta. All right. So the radical's gone. That was one of the things we needed to do. Now what? Okay. So now I get what? What do I do with that? That is the most convenient thing that's happened today. So the integral of secant theta tangent theta is secant theta. And since it's been pointed out that the web work asked for it, let's actually finish by making this giving a function in terms of x. So I want to undo the substitution now. So how can I do that?
Solve for theta first.
Okay, using what?
X substitution.
So if x equals 2 tangent theta, then how do I start isolating theta?
Divide by 2 on both sides.
So x over 2 equals tangent theta.
Then you take the arctangent of theta, or arctangent of x squared to find theta.
Theta equals arctangent x over 2. So I get this 2 secant of arctangent x over 2 plus c. Any questions? So, I mean, about this example or anything else we've done with trig substitution, kind of a strange thing, obviously. Anything at all we want to go over before we go?
Can we go over that, the one, like,
the Weber. It's like, just like something similar where it's like the longer version. We're using like the two.
Ooh. Yeah, hold on, let me get a new slide. Okay. What's the one the web work look like? Do you remember?
Yeah.
I can give you a push in the right direction.
If g of 1 equals -4, and then g of 5 equals 10, well, from 1 to 5, g of 1 dx equals -7.
G of 1 dx?
Yeah, g of 1 dx equals -7.
That's kind of a. Are you sure this doesn't say G of x dx? Okay.
Oh, sorry. Evaluate from 1 to 5 x g on of x dx.
Okay. Is this from? Oh, this is from 6.1.
Yeah.
Okay. All right. Good question. So, given all the stuff we know, can we find this other integral? Any ideas how to set that up? Okay. So I think this is from the section that's integration by parts, right?
Mhm.
If I try this method here, if u equals x, then what's du equal to? And what's v equal to? G of x. And if I use that, what does this integral become? X times g of x.
Minus.
All right. Do we have enough information to? Okay. So I believe this thing right here is given to you, right? That should be -7. But how do you handle this?
You do 5 times g of 5 minus 1 times g of 1.
That's basically it, yeah. Is that, and this is very, very strange because you're so used to doing integration, you know, regardless of method, you're so used to doing integration knowing what the function is. I'm not telling you how it's defined. But even though you don't know how it's defined, you can still set up integration by parts. But yeah, I think the most mysterious part is trying to figure out how to evaluate xg of x from at 1 and 5. So hopefully that helps. What else? Go ahead.
So do you not use that -7?
No, you absolutely do. I just didn't. Sorry, carried this down, and then this becomes minus -7. But yeah, that's part of it. All right, so that is all I have for you for trig substitution. We'll get into new integration stuff on Wednesday. There are due dates coming up for stuff. I think something's due tonight. Okay. And then when's 6.2 due? 24th. So that's Wednesday. Okay. All right. Thanks, everyone. Oh, a reminder, I have office hours this week. So the MCC is now open. I won't be up there today, but is what? Yeah, it's directly upstairs. So room 303 on the 3rd floor.
Have a doctor's appointment on the day we're doing test review. So is there
Okay.
anything I'm like missing, or is it just like people asking?
It's a Q&A, so I'll record that
record it?
session.
Okay.
Yeah, so
Okay.
you won't get to ask your own questions that day, but keep that in mind. Like maybe office hours that week sometime
Yeah.
we can get together.
Okay, thank you.
But yeah, I'll record it. Hey there. Yeah. Okay, good.